Thank you. Hello and welcome to chapter 13, the final unlucky chapter of Introduction to Statistical Learning in Python. We've finally reached the end of the book, and this chapter is on multiple testing, so hypothesis testing. And the chapter does a very brief review of hypothesis testing, doesn't really go into the hows or the whys, but does a quick overview and then jumps straight into multiple testing, which is when you're doing many hypothesis tests and you don't want to make too many type 1 errors. So there's quite a bit of assumed knowledge, I guess, for this chapter, and it's slightly out of step with the remainder of the book, where the remainder of the book has been much more focused on statistical learning and prediction, whereas this is much more about inference and hypothesis testing. So it's focused around p-values, which get a lot of heat from various corners of the statistical community over the previous 5-10 years, mainly focused around their misuse and people using them in situations when it perhaps doesn't make sense, or just blindly following this p is less than 0.05, therefore this is a significant result, which has led to quite a lot of bad science being published, or things thought true that just really weren't when proper statistics was done, or larger tests. Replication has been a problem. Yes, so hypothesis testing is used when we want to answer simple binaries, or like yes/no questions about data. And it gives an example of, is there a difference in expected blood pressure of lab mice in the control group and expected blood pressure of lab mice in the treatment group? So does this treatment, whatever it was, have an impact? Does it change the mean blood pressure either way, up or down? And there's a fairly standard process that we go through for doing this sort of test, which is we first define what we call the null and alternative hypothesis. So the null hypothesis is usually like the boring one, and it's the one that we're trying to reject or gather evidence against. So in this case, the null hypothesis would be that the two means are the same. There's the treatment that has had no impact, and the mean blood pressure is exactly the same between the control group and the treatment group. There was a footnote here, but I assume this is fairly common knowledge that the control group is the one that didn't receive the treatment, and the treatment group is those that did. And so your alternative hypothesis is that there is a difference. There does exist a difference in the means. And once we've got these like more formal hypotheses, we construct the test statistic, which throughout the chapter is called T. The exact form of that test statistic depends on what exactly you're testing. So in this example, we are testing for inequality of means, which we do using a two-sided t-test. And it's called a two-sided t-test because this statistic follows a t-distribution. If you're testing inequality of variances or other parameters, you will end up with quite often like a chi-squared distribution or an F distribution. So yeah, the distribution of this underlying statistic really depends on the hypothesis that you are testing. And the basic line goes that if you get a very large absolute value of t, you are providing evidence against your null hypothesis. So you probably will remember from any introduction to statistics class that you've done, or any statistics that's been done before, is that you never say that the null hypothesis is false and the other one is true. You're always just providing evidence against or suggest rejecting, because you can make mistakes in this hypothesis test. You're just gathering evidence. You're not proving either way. And this is the sort of graph that you'd get. You've got your underlying null distribution of your test statistic, and your test statistic value in this case was 2.33, and it's a large absolute value, which then you can decide whether or not to reject or accept the null hypothesis. I've skipped some steps. Yeah, this plot is just to show that where the t-statistic lies within this distribution. And in this picture, the density function is the standard normal, so a normal distribution with mean 0 and standard deviation 1, or variance 1. And that's because the t-distribution as the sample sizes in your treatment and control group, as they get large, this distribution is really well approximated by a normal 0-1 distribution, which makes this nice and easy. And as the caption says here, 1% of the area under the curve falls to the right of the vertical line, so this little sliver here. And so there is only 2% chance of observing a normal value that is greater than 2.3 or less than minus 2.33. So you can think of mirroring this line on this side when you've got this little area as well. And that's because we're looking at absolute value. We're looking at not equal to. We're not looking at greater than or less than, which would be one-sided. Okay, and from there we can compute the p-value. The p-value is defined as the probability of observing a test statistic equal to or more extreme than the observed statistic under the assumption that H0 is true. So that's quite a mouthful, and I think this is where the confusion comes in over what exactly a p-value is. But the reason that we create a p-value is that it allows us to have a number between 0 and 1, a probability, that is much easier to communicate than just a point value on your underlying null distribution. So here you've got 2.33. It gives an example in the book where it's like the t value, the test statistic might be like 17.3, but you don't know whether that's large in an absolute sense because you don't have it relative to anything else. The p-value gives us a way of saying whether that is a big value or not. And then from that value, we can decide whether or not to reject the null hypothesis. So like I said earlier, a standard value is like 0.05. So is this probability less than 0.05? And if it is, then you reject the null hypothesis. But that 0.05 value is really very arbitrary. You could choose any value, and it's often recommended to choose multiple different values to show how that is impacting the answers that you're getting out. And again, it gives an example in the book of physics that p-values want to be less than 10 to the minus 9 or something ridiculous like that. So it really depends on what you're modeling, where the data's come from, the data generating process, how extreme this value has to be until you do reject the null hypothesis. Okay, so that's the basics of the process of a hypothesis test. But of course, you can get things wrong. And it produces this table of type 1 and type 2 errors. So a type 1 error is that you've decided to reject the null hypothesis. You've got evidence to reject the null hypothesis, when in fact the null hypothesis is true. So you're saying your treatment, your intervention works, when in fact it doesn't, which is obviously quite problematic. Or on the other side, there's a type 2 error, which is when you decide not to reject H0, so you don't have enough evidence to reject, or don't have enough evidence to say that the treatment does have an impact. But then in fact, the treatment was having an impact. So in the book, it says it's generally seen that type 1 errors are the worst of the two to make, because you're saying that something has an impact when it doesn't, or there is a difference when it's not really there. And it's similar to what we've seen earlier in like a binary classification. You're making a false positive. You're saying something is true when it's not, or equally, type 2 is a false negative. You've got that the wrong way around. A key point here is once the hypothesis test is performed, you know which row of the table you're in because you know what your decision was, but it's impossible to know which column you're in because we don't know the truth, and you can never know the truth. Okay, any questions, comments, thoughts on that section before we dive into multiple testing?
Not so much questions, but I know from psychology we've had very similar, we've had these problems of resonate a lot in terms of the psychological schools and research, especially with regards to p-value controversy. And also the type 1 and type 2 errors are something very finicky with a lot of psychology scientists, in terms of like rejecting the null hypothesis but then another paper will come out being like, no, actually, this was like essentially too assumptuous, essentially too big a claim to make. So I think that this chapter, when I read it, was like really relevant in terms of how the current research is struggling to strike a chord in the scientific community, how to balance these assumptions with rigorous statistics. So I just thought it was very interesting. And I think it's quite a polemic issue that a lot of the science community are facing still today.
Interesting. I think I'd be interested in, first of all, why you think these errors were being made, or why you think this is the case in psychology in particular. Because, yeah, from what little I've read about it, it seems to a lot of it is coming from, let's say, those sciences. And my other question would be, in your education in psychology, were these things discussed, or how were you taught this? Were you taught like a standard statistics course, and that was sort of acknowledged but ignored, much like it is in this chapter? It feels it's like this is a problem, but let's not worry about it here. Or was it faced much more head on?
Love the questions. I'm actually going to work backwards a bit. I'm going to address your second question first. So yeah, we actually dedicated a whole, not only just module, but essentially a whole term to statistical learning. So baseline statistics, baseline understanding of like stats 101. So we went through a lot of like lessons about obviously p-values, effect sizes, but also the statistical understandings. Very sorry, I think someone's shouting outside. Classic London. Welcome to the London experience. And it went through baseline, like very basic statistical methods for basically how to conduct an experiment through the scientific method using statistics. So you got given your basic SPSS. We had like basic understanding of how to handle quantitative data. It wasn't super in depth. It was basically like, here's stats 101. Here's how you can not conduct a totally abhorrent experiment. Having said that, this was a discussion being made by like people running my course, and it's actually one of the reasons why I chose to diverge from like experimental psychology to computational, because I think some of the issues that are stemming from type 1 errors like false positives is, one, obviously you have unfortunately like publication bias, because journals are going to publish statistically significant results, and researchers do feel pressure to find the p-value to be less than 0.05. So p-hacking, unfortunately, is huge in psychology, unfortunately. There's, I think, a lot of memes across like academic Twitter, which is like a terrible resource, but there's a lot of memes and like screenshots where it's like, what the hell has this person done? But it happens. And one thing you'll see when you read a psychology paper as well is that obviously, because we don't really know that much about the human brain still, is some studies will use small sample sizes, and obviously the small sample sizes come quite low statistical power. So it means, let's say you're looking at like 10 or 11 individuals trying to understand the effect of a drug, as an example, a drug on their anxiety and depression side effects. They might get the p-value or the statistical result they want, but that, let's face it, like lacks a lot of power to detect actual impactful effects. So when this significance, when they do find p is less than 0.05, sorry, this is essentially found really by chance if you think about the sample size, but they still get published. And I think there is a demand both like in the academic field of things and like the theoretical and finding novel, surprising findings, like exciting new findings, like, oh, this we found, we can make this very extreme premise or conclusion about the brain on this study, and it's not always the case. And I think there's a lot of replication issues. So it's hard because then your false discoveries don't get adequately challenged. And yeah, so with computational psychology, it's a bit more obtuse, but it means that what the field tries to do is use, I guess, a bit more statistical modeling and computational modeling in general to try and challenge these arguments and these theories. And yeah, I think small sample sizes is one big issue. So, you know, you don't really have the statistical significance in the paper because you just don't have the effect size you really want. So yeah, I think it's a mixture of things. Measurement issues as well, for sure. I think sometimes because there's such an inherent subjectivity to qualitative experience, qualitative descriptions, semi-structured interviewing, that can really obscure your effects. And again, that was something that made me want to be like more structured. And I went down the computational route and cognitive science route through these discussions. So I think it was good to have these discussions to expose the limits of what we face in psychology. Because I was like, oh, actually, that makes sense. Maybe through a more computational approach, or a statistical approach, we can hopefully start to improve these limitations. But sorry, that was a very long-winded answer, but hopefully that gave a bit more insight into why psychology is facing a lot of research issues at the minute.
Yeah, it's very interesting to hear your perspective. I think it's kind of like just really sad in a way that that's the way the academic system works, and that it works for the individual to get published and get the highly cited, you know, papers and getting the news journals, news articles and what have you. But then really it slows science down because people are then trying to replicate, not being able to replicate, so wasting time trying to work out why they can't replicate, and then not getting published to say that that was wrong because nobody likes negative results.
Oh, exactly. And I think, again, as you say, it's so anti-science because we should embrace negative results. We should say, actually, these findings indicate that we can't make a definitive conclusion about X, Y, Z, but this opens up more avenues to research this aspect because maybe this is a reason why this phenomenon isn't taking place because ABC. And yeah, I mean, I always used to think, oh, I remember starting when I started my master's, I thought, oh, this sounds a bit conspiracy theorist, like people want to try and get published. But then when I watch like my husband, and he's still in academia, he's doing postdoc, and all the gatekeeping and the politics, I'm like, no, and that's in chemistry. That's not even, that's a you'd think there's a lot more maths and quantum physics involved in the stuff he does, which arguably is, I guess, you have actual proofs. You could think, oh, surely there's it's difficult to argue against certain quantitative concepts versus a qualitative subject like psychology. No, still very political. So yeah, that even chemistry is having its own issues at the minute.
Yeah, I mean, these problems certainly aren't unique to psychology. I remember getting told about an example in mathematical biology, where they'd come up with some theory and got some evidence for it, and they managed to get like a really big paper in Nature. And then like 10 years later, it was the same group that basically said that we were wrong and here's how it actually is. And they got like another paper in Nature.
Oh my gosh. Yeah.
That's the way to play the game, that one.
Oh gosh. Yeah. That doesn't surprise me. That doesn't surprise me. Every time my husband comes back, he's trying to get a paper through, and he's like, "Reviewer 2, no." And he spends the whole day just angry at reviewer 2. like reviewer 2 is the bane of every academic's life, I swear.
Totally. Funny. Anyway, back onto a nice little diversion there into philosophy of science, philosophy of p-values and what's going wrong.
The existential crisis of science that we face today.
Yeah. But none of that will help us do multiple testing, which if you don't like p-values, you're about to start doing thousands of them at once and make even more errors, likely. So the idea behind multiple testing is when you've got big data, you might have a lot of questions you want answering and a lot of hypotheses that you want to test. But doing that, you will, by random chance, end up making too many rejections, too many type 1 errors. And a really simple illustration of this, it also gives a nice one about stock advice in the book, which I think is a scam that's actually been run before successfully to get people to give money. Because you email enough people with your predictions, and by random chance, you'll be telling one person the correct advice. But you can see this in even a fair coin. So if you toss a fair coin 1,024 times, 10 times each, on average, one coin would come up all tails. And that's because the probability of flipping one tail is obviously a half if it's a fair coin. And so 10 tails is that 1/2 to the power 10, which is 1/1024. So you're expecting 1 in 1,000 basically to come up tails. And so it's the same idea when you're doing multiple testing. If you're testing a huge number of null hypotheses, you're bound to get some very small p-values just by chance. And this leads us on to what we call the family-wise error rate. And so here we've got a similar table to what we had above, but instead of just doing the one hypothesis test, you're doing m of them, and you make V type 1 errors, W type 2 errors, and then U and S are when you've correctly done. Forgot that right? Yeah, U and S are when you've got the answer correct, basically. I didn't think this table was that useful. I think it's just introducing notation for later on. But the family-wise error rate is basically the probability that V is greater than 1. So the probability that you're making more than one type 1 error in this set of M hypothesis tests. And doing that at a level alpha, you can work this out. So the probability of V being greater than 1, if you look at the complement of that event, it's the probability of V equals 0. So 1 minus, that's equivalent to 1 minus the probability of V being 0, which is the probability that you do not falsely reject any of the null hypothesis, which itself is the intersection of not rejecting or not falsely rejecting any of the jth null hypotheses. And a big assumption here, but if your tests are independent, then you can pull this intersection outside of your probability measure and turn it into a product, and you get 1 minus the product of 1 minus alpha, which is the probability of making a error here and falsely rejecting H not J. And you can plot this for different values of alpha, and obviously M is the number of hypothesis tests that we're doing. And so you can see at different significance levels how this curve changes, how the family-wise error rate increases based on the number of hypothesis tests you are testing. And the dashed line is 0.05, so that like standard value that you're testing against. And you can see how many hypothesis tests you have to run until you'll get, you'll make that error basically. Okay, I pasted this table in of the data for these fund managers, but I don't know if I actually put anything in later on that referred to this, so I'll just skip this for now and it's there if we need to come back to it. So we've got this family-wise error rate that you're basically definitely going to make, and it's how do you control this error rate, given that you're going to do multiple testing, you're going to do many hypothesis tests, and there is 4 methods that we do in this chapter. 2 are very general and 2 are for specific use cases. So if we start with the more general ones, we have the Bonferroni correction and Holmes step-down procedure. So just like before, you've got M hypotheses that you want to test. So you've got all of these null hypotheses, and this AJ is the event that you make a type 1 error for the jth null hypothesis for each of your M hypothesis tests. And this probability of rejecting at least 1 is the probability of the union of the type 1 error for the jth null hypothesis. And from like your basic laws of probability, the probability of a union is less than the sum of those probabilities. So that then gives us a bound, because to keep the family-wise error rate below alpha, we can just set this to being less than alpha over M, and then we have M of them. So then M times alpha over M, you get the family-wise error rate will be less than alpha. Cool, so that's pros of this method. It's really straightforward, very easy to implement, and it works. But the downside is that this inequality is really not tight. This can be a massive overestimation, which means that you're being more restrictive than you need to be. And so we look to Holmes step-down procedure, which is a way of trying to make this a bit tighter and not having to be overly conservative, basically. So this is the algorithm. So you've chosen your alpha, which is the level at which you want to control your family-wise error rate. You compute your p-values for all of them, for all of your null hypotheses. You order them, and then set this value, which is the minimum value that your, well, the smallest index in your list that is greater than this value here. And then you reject all the null hypotheses for which your p-value is less than this critical value of PL. And it demonstrates the different methods here in this figure. So these are ordered by size, which is why all of these go bottom left to top right. And we've got two null hypotheses that are true in black, and the false ones are all in red. And you can see, what can we see? Here you go. The Bonferroni procedure rejects all null hypotheses that fall below the black line. So these are three different scenarios, basically, of where these p-values could be. And your Bonferroni procedure is this black line, where you're rejecting 1, 2, 3, 4, 7, and accepting the three above. And your Bonferroni procedure is this blue line that obviously changes depending on the number of p-values, whereas the Bonferroni procedure is just constant. It's probably better to look at this one when you basically, this illustrates the benefit of using the Holmes procedure rather than the Bonferroni, where here, if you'd done the Bonferroni correction, you'd be rejecting all of these and making all these errors, whereas if you do the if you do the Holmes step-down procedure, you get the correct answer for the two true ones and you reject all of the false ones. So that's cool. That's really good because they both make no assumptions about the null hypotheses, and they're very broadly applicable, but they can be improved upon if you make some more assumptions about your null hypotheses. And that's the two special cases that the book gives here. It didn't give any information on how you actually do these methods. It just gives you the scenarios for when you might need to use them. So I guess that's good to know, to have in the back pocket, if you like, of, oh, in this scenario, I can use this method. Now I'm going to read into how to actually do that method. So the first one is Tukey's method. I don't actually know if it's Tukey or Tukey, but the inventor of the box plot, I believe, quite a big name in statistics. And you can use this method for when you're forming pairwise comparisons in the hypothesis tests. So are any of the means different? So as the example in this data set was like, are any of these managers performing differently? You're doing a pairwise comparison between each of the managers. And obviously you've lost the independence between your hypothesis tests there, because if you know that, like what was the example I've given? If A is greater than B and B is greater than C, then that tells us something about the relationship between A and C. And it's the same sort of thing here. Once we know the difference in different sets, we can use that information later on, basically. That's when Tukey's method comes in. The other case for Sheffey's method is when you're comparing groups of individuals in the data. So here you want to see if the average performance of manager 1 and 3 is the same as the average performance of the group of the rest, basically. What I think is interesting here is this is like the only test that you've done. It's not like the pairwise ones where you can very clearly see you're doing multiple testing. Here it looks like you've only done the one test, but because you chose these groups based on the data in that table, so you've looked at this data here and you've been like, oh, well, 1 and 3 look significantly different. I'm going to group them and then group the others to see if there's a difference there. That's already some sort of form of test. And so you risk running into the trap of doing multiple testing without really realizing it. But in this case, Sheffield's method can be used to control the type 1 error. And again, it doesn't give much information on how to do these methods or how to get the alpha level of each of these methods. It just says when you might want to use them. So I'll leave that as an exercise to the viewer if you're interested in that.
I'll also say, like, from my, again, just past experience, like, obviously in psychology, we've had to use things like Bonferroni and Tukey's method quite a bit for things like pairwise comparisons, specifically with Tukey's, and with analysis of variance. And I think Tukey's is good when it's good, but I'd say something that does not even bothers me. It's a very specific tool, because I found that if you need basically equal group sizes, right? And essentially you need that. There's a restrictive assumptions in that when you violate the homogeneity of variance between population groups, you end up skewing your findings quite a bit. So I find it's one of those things where, like, I call it like the Goldilocks scenario, like the Goldilocks the Goldilocks comparisons, when you have that specific specific use case where you can use it, it works really well. And I think it's been a while since I've used it. But I do think I found that I used it quite a bit for specific period times where you have those comparisons that share like error terms and they aren't independent. So it made it a bit less conservative than other correction methods that obviously assumed independence. So when it works, but I found I only used it almost not necessarily so rarely, but so specifically. But I will say when it works, it works. But it's one of those tools to have in your back pocket, but just be aware that it's kind of that period where, pairwise comparisons, and as long as you don't violate the homogeneity of variance, otherwise, you'll find that it gives you quite skewed findings.
Interesting. I've not come across these like correction methods before. I think because I've never done a formal course that got as far as ANOVA, which I think is where this is more common. But yeah, it's good to know that these are quite special cases. Like in the book, it probably doesn't make clear how special they are, and it also doesn't list all the assumptions, like you said, the homogeneity of variance.
I think, like, again, like, I'm not saying it is only in psychology, but I think because in psychology you have so many multiple outcome measures, you have to have all these random weird correction tools for when you're performing your statistical analysis. Otherwise, you can basically, essentially, not even purposefully, but you can end up saying something or claim something that isn't actually true, as we've discussed earlier. So it's a real balancing out between conservative and not falsifying your scientific output, but also trying to actually create a meaningful output for your experiment. And I think one of the limitations is that because you're not always going to naturally have situations where you're doing pairwise comparisons across different dependent variables, it is difficult to use it almost organically. I ended up using it either for, like, especially like a statistics exam, to be like, they literally would ask you specifically to use this method to showcase you just understand the steps for doing it. Or I think even for very specific not even behavioral experiments, but almost like online experiments in our first year when it was COVID, actually, and we couldn't do in-lab behavioral stuff. So it ended up being like such weird use cases, but when I used it, it worked pretty well. I just couldn't use it all the time.
It was a bit artificial sometimes when you're like this.
Yeah, exactly.
Yeah. Cool. Interesting. From here, the notes get even more sketchy than they've been up to now. So please, if I say anything false or I'm not making any sense, do just call me out on that. But we move on to the trade-off between the family-wise error rate and the power of your analysis. So power is the number of false null hypotheses we reject divided by the total number of false null hypotheses. So as power increases, the family-wise error rate increases as well. And that's what this plot's showing. So as you're doing more and more tests, more and more hypothesis tests, the different lines are different numbers of hypothesis tests, but as you increase the power or try and increase the power, your family-wise error rate will just go up and up and up. And so example here is you've got 90% of the null hypotheses are true. You're trying to look at, the power. So the fraction of false null hypotheses that we successfully reject as a function of the family-wise error rate. So if M is very large, we should be willing to tolerate false positives in the interest of making more discoveries. So you're trying to be less conservative, because otherwise you'll just basically remove any positives whatsoever. And so rather than looking at the family-wise error rate, we look at the false discovery rate, which is the ratio of false positives to total positives. So it's like the number of mistakes you're willing to make in the interest of keeping in the good results. And that is, so the false discovery rate is the expected value of, I forgot what the P stands for now, false discovery proportion, I think, which is the expected value of V over R, where V was the number of type 1 errors and R is the total number of rejected hypotheses. So when we control the false discovery rate at a level of 20%, say, we're rejecting as many null hypotheses as possible while guaranteeing that no more than 20% of those rejected null hypotheses are false positives on average. And again, the book gives an example of if you've got a whole genomic sequence and you're trying to see whether it's having an impact on something, you might be willing to make 20% of errors because you've got time to check all of them. And the more energy you're willing to spend to investigate further those ones that you reject, basically governs the false discovery rate you're willing to put up with. And the book gives a procedure for controlling the false discovery rate, the Benjamini-Hochberg procedure, which looks a little bit like the home step-down method, I thought. The home step-down procedure with a max instead of a min, and obviously this value is very different to what it was in the step-down procedure. But similarly, you specify a level at which you want to control the false discovery rate, you compute p-values, you sort them, and then you find the index of the one that is the maximum that satisfies this bound, and you reject all of the ones below it, or for which the p-value is smaller than that. So we get a very base R-looking plot in which we display a set of 2000 p-values for this fund data, which was the one about the fund managers earlier on. And green lines indicate the p-value thresholds corresponding to family-wise error rate control from earlier on using the Bonferroni procedure at different significance levels. And where are we? The p-values, the orange lines indicate the p-value thresholds corresponding to the FDR control, so the false discovery rate control via Benjamini-Hochberg at the different levels. And so at 0.1, which is this middle one, you can see that 146 null hypotheses are rejected. Is that because they're the ones? Yeah, because you're looking at the maximum intersection with this line in each case. So there's no intersection here. You're intersecting there, and then obviously intersecting here, and you're rejecting everything below it in both cases. So if you're controlling at 0.1, you reject 146. If you're controlling at 0.3, you reject 279. So again, you've got in the middle, you've got a 10% false discovery rate. So 10% of these are likely to be type 1 errors. And on the right, you've got a 30% false discovery rate. So 30% of these are likely to be false discovery, likely to be type 1 errors. I didn't go deep on this section, as you can probably tell. So yeah, it wasn't immediately clear when you'd be using this or when you'd want to be looking into this. I guess it is this case where you're doing many hypothesis tests and you don't want to reject too much. Okay, and then the final section of the book, it says, is a little bit more technical, but we'll give you a brief overview on it. Actually, literally is just these 2 lines before, because I didn't dive into the example. So if you remember right back at the beginning where we had our test statistic T and we were testing for inequality of means. And when you're testing for whether the means are equal or not equal, you know that the test statistic underlying that follows this a T distribution. The nice thing about the T distribution is if your sample sizes are big enough in both your groups, then that T distribution is approximately a normal distribution, which is easy to get results from for your p-values. But what if you're doing something a bit funky in your tests, or you're testing something a bit odd, not one of these standard ones that's going to end up with T distribution chi-squared or F distribution? You basically need a way to create this null distribution of your test statistic because you don't have a theoretical answer. So yeah, one case could be that you're testing something a bit different, or alternatively, it could be if your sample size is so small that your T distribution can no longer be well approximated by the normal distribution in the case of earlier on, and you're going to have to do something different. And the rest of this chapter basically says that that's okay. You can still do inference, but you need to approximate this null distribution of the test statistic first so that you can get a p-value and then decide to whether to reject or accept your hypothesis. And yeah, I started writing out the example and then thought that's enough of that, and I'll just leave that there. But yeah, have a deeper read if you're more interested. But that's multiple testing. That's it. It's the first time I've ever finished within the hour for a chapter and done it in 1 week. So yeah, thank you for attending.
Nice one, Tom.
It's been a very long time. Yeah, if you've been following on YouTube, I'm pleased you've made it this far. Congratulations and well done. I'll stop the recording there if I can find Zoom.
I put you in, I wrote finish.